Mr. Arnaud Roux is head of European Sales Department of 3D Ceram since 2016. After obtaining a Master of International Business Management in France and a Bachelor of Business Administration in Scotland, Mr. Roux worked for Legrand and Airflow before joining 3D Ceram Cinto. In 19 years since its creation, 3D Ceram became a world leader in 3D ceramic printing, selling 3D ceramic printers all over the world and having clients covering a broad range of applications. So let's take Mr. Arnaud Roux.
Bom dia a todos. That's all. I will continue in English. Thank you very much, Italo, for the presentation. Thank you for all the organizers for this event. It's a great thing, I think, to have additive manufacturing for technical ceramics in Brazil, where I'm sure there is an important potential. So my name is Arnaud. We have a small stand over there, so you are more than welcome to see the different parts that we are showing. We cannot bring printer, but we bring parts, so you can see what we are able to do. Today, I'd like to focus on two technologies after the conference of Professor Colombo. One is called SLA, the second one is called MAT. It's mainly filament or extrusion-based technology. Here we have audience of university, so we have machines more for prototyping, developing new materials, but we have also the possibility with SLA to switch and scale to industrial production. So that's what I'm going to focus also today. One word about 3D Ceram. We are a French company based in Limoges. Limoges, you probably don't know, it's a small city in the center of France, in between Paris and Toulouse. It's famous for ceramics, traditional ceramics, especially porcelain. So tableware, we have been producing porcelain for the last 200 years. But since 40 years now, we are also working a lot in technical ceramics. And I'm focusing in technical ceramics because we have a technical research center over there called EESC-USP. Maybe some of them knows. They developed in 2000 this technology SLA, so more than 24 years ago. So we can say that we are pioneer really in additive manufacturing of technical ceramics. All these red points is where we have partners worldwide to represent our company. Here in Brazil, I'm working with Farco company based in São Paulo, reselling several brands of additive manufacturing equipment, metal, plastic, and ceramics with 3D Ceram. Here you see an image of 3D Ceram building. It's a new building. We are producing in Limoges our printers. We are part of Cinto Group. That's also a very important point. Cinto is a Japanese group with more than 4,000 people in the world working in equipment for foundry. And in Brazil, it's also Cinto Brazil existing here for all the equipment relating to foundries. That's a big group, and it's important for us to be supported by such a group to expand our internationally our business. What do we propose? Quickly, okay, we are a process provider. It's not only equipment of printing. You know, when you print ceramics, as Professor Colombo explained, you have printing first step, but you have many other steps after to obtain the final part. So we accompany our customer on, of course, printing equipment, but also firing equipment. We are not producing any furnaces, but we can supply or recommend furnaces. And as Nespresso business model, we propose equipment, but we propose also consumables, okay? The small capsule of coffee, here it's a liquid slurry that we deliver with our printer, ready to print, okay? So that's what we call the mix. Software, very important. We worked on dedicated software because we know that 3D it's a new technology. So we worked on a specific software to help customers, for example, to create support, to understand better how to position the part on the building platform. And that's key points to have quick success. And services, it's just accompany our customer, make training, installation, maintenance of the equipment, so the customer is not alone when he has the machine. We support him thanks to our team in France, but thanks also to our local team in each countries, and here with Farco in Brazil. Just one word about our history, because it's important for you to understand how was created 3D Ceram. So I told you in 2000, Professor Thierry Chartier developed this technology of stereolithography. Between 2000 and 2005, it was matured, but it was acquired by a technology transfer center called CTTC, so Ceramic Transfer Technology, and this they were producing parts until 2009, when our two CEOs decided to buy the patent in 2009 and create 3D Ceram. And between 2009 and 2015, we were using our printers that we developed ourselves. We were using our raw material to sell parts. So we were doing service printing to all the companies who were willing to buy our parts. So we were receiving demands from universities who wanted to check the parts, dental industry, aerospace business, but also semiconductor business, luxury demands, very wide range of application. And I'm going to present also what are the application and what are the markets behind additive manufacturing of technical ceramics. 2017, Cinto acquired 3D Ceram, new shareholder, a strong shareholder. 2018, 2019, we scale up machines from a small printer. We developed bigger printer because we believe that in the future, the industrial customers, they want to make production with additive manufacturing, not only making few prototypes. And in 2022, 2 years ago, we bought a company called Tivari Scientific Instruments. It's a startup company who developed this M80 machine, a small desktop printer that I'm going to present you in this presentation. So why industrial scale is needed? One focus about the market and what we see in figures. On the right side, left side, you have the trends of the global technical ceramic market, not only additive manufacturing, but all technologies in this graph. We see that it's strongly increasing, very constantly increasing growth in the coming years, in the next 10 years. On the right side, you have the potential of additive manufacturing market for ceramic. And you see that it's also very growing fast. So we have a bright future for additive manufacturing of technical ceramics. That's important to know that, and we can feel it because we have been in this market for the last 10 years, and we see more and more industrial customers coming, asking for parts or asking for equipment. This graph is just to show where we have more demand. So aerospace and defense is clearly the important part, 40%. Ceramic properties are very interesting in this businesses of aerospace, defense, where you have very difficult environment, high temperature or very low temperature, high electrical resistance needed. Healthcare is a second interesting business sector, I would say, clearly for the properties of biocompatibility of ceramic. And we see after automotive, consumer goods and electronics, constructions, but it's mainly industrial needs, and I will explain you a little bit more which clearly application ceramic additive manufacturing is interesting. So with SLA, I will focus now on SLA technology. What is SLA? It means stereolithography. Here you have example of how it works. On this drawing, you see that you have the optical chain at the top, the build platform in the middle, the blades to spread a layer, and the build platform is going down. So it means at the beginning we are mixing ceramic powder with photosensitive binder. Okay, it makes something liquid. This slurry you put into the printer, and the machine will do a layer, a thin layer. For example, in alumina today we do a 50 microns layer thickness. On this layer, a UV laser will polymerize the part you want to print. The build platform goes down, 50 microns down, another layer 50 microns, and again the laser polymerizes the part. So we print the part from the bottom to the top. So we say it's a top-down process, okay? It has many advantages because gravity is playing with us, so we limit the quantity of support, and limit quantity of support is very important with ceramic to reduce stress into the part, because you need to cut the support or remove it after printing or after sintering. I'd like to insist on this machine, which is the smallest one that we have with SLA technology. It's called C100 Easy Lab. It has a platform of 100 millimeter by 100 millimeter. That's mainly the machine we are distributing and selling more for universities, institutes, research centers, or R&D department of industrial customers who wants to enter into the business of ceramic additive manufacturing. With this machine, what is interesting for you is, for example, you can develop your own slurry. If you want to develop one material which is not available, or you want to test one powder, you can create your slurry and try to print it on the printer. You have a possibility to create your own printing parameters, your own recipe on the machine. So you can have open access to put the different parameters of printing on the printer. You can also reduce the platform if you want to 50 millimeter by 50 millimeter to reduce also if you just want to do a reactivity test with the printer to check a material. With only 10 milliliter, you can do your test. Another important development that we did, and Professor Colombo said it's important to have multi-material possibility. So we developed a machine, we called it C101 Hybrid. It's multi-material printing. It means that we can print ceramic, but we can print a second material altogether. So that example of parts and draw a picture on how it works. We have on this machine 2 materials possible to print together, but we have even a bigger machine where you have the possibility to print 4 materials all together. It's good, it's nice. You have the possibility to print several materials, but printing is not really the issue, I would say. Clearly, it's how you are going to sinter and co-sinter several materials together. So today, yes, equipment we can deliver, but we don't have at 3D Ceram the know-how how to co-sinter, for example. So it means that our customers who bought these printers, they know how to co-sinter the materials they want to develop. And that example of parts we did with sacrificial material inside. And at EESC, our university in Limoges, they were able to work on HTCC and LTCC, where they managed to sinter alumina with tungsten. But it has been most of the work on how to co-sinter. Important point with SLA, the possibility to scale on bigger printing. So that's interesting for industrial customers. You can develop and prototypes with a small machine, but you can scale on bigger machine. So it means that, for example, you see on this small machine, you have 1 laser working. On the medium machine, 320 by 320 millimeter, 2 lasers working. Exactly the same laser, but 2 lasers. So you print faster. We developed even a bigger machine, 600 by 600 millimeter, with 4 lasers altogether. It's clearly focused on production. So production of big parts, it's possible, but also production of lots of small parts with exactly the same quality. I insist on that because it's same laser, same slurry, same consumable, and exactly the same technology with a blade to make each layer. So just examples of time of printing, for example. On the small machine, this small parts here, 4 parts printed in 1 hour and 20 minutes. Here on the medium machine, 48 parts in 6 hours. And on the very big one, 112 parts in 12 hours. I have this part, if you want, on the booth, so you can have a look of this part in alumina. So we say mass production. No, it's not mass production, because mass production, it's what you do with injection molding, with pressing. Here, you can make millions of parts. It's more customized production in high quantity of parts, but we are not talking of millions of parts, we are talking of thousands of parts. So what are the materials today ready with SLA on our portfolio? Oxide material, non-oxide material. So in oxide, the standard ones, alumina, zirconia, silica-based material also, translucent alumina, hydroxyapatite, tricalcium phosphate, corderite also. And non-oxide, it has been also developed in the last 4 years now, aluminum nitride, silicon nitride. It has been a specific development because it's dark powder compared to oxide, and dark powder is a little bit more difficult to print. And you see here, we do not propose silicon carbide, for example, because at the moment with SLA, it's not ready. What is important for universities, technical research center, is all what you can develop. And here is examples of materials developed by our customers, universities. Example, Create 3D. I've been developing with university in Singapore, Spinel and YAG. Skoltech in Russia, before the war, developed Regolith. Matéis in Lyon, in Lyon in France, has developed zirconia doped with ceria. So that's very important because we are really willing to create collaboration with universities to develop new materials. So that was the Spinel developed with NTU University in Singapore. So transparent ceramic, very interesting, mainly in the defense industry. We saw this morning Itria printing. And in the dental field, Matéis worked on zirconia doped with ceria, where clearly when you add alumina particles and aluminate platelets, you have a very good, you improve the plasticity of the material, of zirconia. I'd like to focus on applications now. It's important because all our customers are coming, okay, what can I do with your printer? What are the markets behind? New world needs technical ceramics. What do I mean? With ceramic, you have ultra high performance material. Very good mechanical property, high hardness, good resistance to wear, abrasion, electrical insulation, and also low density. And in the new industrial world, we have new energy, we have new mobility, new space also, new defense, and new health. So it's clearly where we have demand. In biomedical, few examples here, cranial implants, sternal implant, knee prosthesis, or dental application. So you see here, for example, dental brackets, where very small parts, where 3D printing is quite interesting to do low volume of parts. You don't have to make a mold. If you need to produce only 5,000 parts, it's interesting to use 3D printing. It's very small parts, so you can print good quantity on one platform. But also in dental, you have zirconia implants, where you have interesting demand for biocompatibility and very good resistance. But I'd like to focus on, for example, skull implants. Skull implant was the first success story of 3D Ceram almost 20 years ago. We developed a partnership with Limoges Hospital, so hospital of where we are based, with a surgeon who asked us to produce a customized implant from a lack of patients after surgery or trauma or a cancer. So with 3D printing, the main advantage, you can make perfectly the implants, and you can even add porosity on the border using hydroxyapatite. So with this porosity, the bone will grow into the implant. And the surgeon doesn't need to put screw to maintain the implant. So that's the main advantage. So that's a real case of a young guy after an accident. It was before, before, during, after. And I have another example. of a woman. So after 12 months, the bone have perfect osseo integration with hydroxyapatite. So that was the first success story of 3D Ceram. I'd like to focus on aerospace now. What we have is, you probably know satellites going very far from Earth, but we have now what we call new space. New space is small satellites, nanosatellites, going at low altitude in orbit, around 400 kilometers. It's smaller satellites. And it has been developed very quickly by lots of startups, and they wanted to go fast. Additive manufacturing is a good answer to react quickly, to produce complex parts, miniaturize also the parts, adding several functionalities in one part. So you have example of a company here called Trust Me. They are doing this kind of thruster, so it's propulsion system, small engine. When the satellite is turning around the Earth, it's also going down a little bit. So sometimes you need to reposition the satellites in orbit, and you need small motors to do that. And in this part, you have a ceramic and alumina part made by 3D printing. So it's already in space, additive manufacturing of technical ceramics. Another example is a company called Anywaves, based in Toulouse, south of France. They are producing antennas, antennas for nanosatellites. They developed a specific geometry, lattice structure you can do only by additive manufacturing in zirconia for the very good property of permittivity of zirconia. And that also in orbit now. So that example, concrete example where in the aerospace business, additive manufacturing is very interesting. Another possibility, I'm not sure you know this technology, but it's in investment casting for precision foundries. When they want to produce this kind of part for aircraft engine in metal, you need a ceramic core inside this part as a mold, as a negative mold. So it means that it's silica-based material. They are going to cast the metal around and after dissolve the ceramic core inside. And for this part, you need porosity. So it's a very specific application. We were not specialists of this, so we developed a joint venture with Avignon Ceramic, a company already producing ceramic cores by injection molding, and now they are also using additive manufacturing to make more complex cores. Because Rolls-Royce, Safran, they are always looking for more and more complex parts, so the metal blades can resist to higher temperature in the engine. Few words about energy. So here I'd like to share with you a European project where we are involved. It's for production of solid oxide electrolysis cells. Here it's clearly on improving production of hydrogen. Hydrogen has bright future, but currently the cost of hydrogen is quite high compared to petrol or gas. So they are working on how reducing cost of hydrogen. To do that, they use electrolysis to produce hydrogen, and they are usually in the traditional method, they use flat membranes in ceramic. Institute in Barcelona works in how if we make a corrugated membranes in ceramic, so with waves, not flat, you improve a lot the reactivity of, and you improve the quantity of hydrogen produced. So that's another example of where additive manufacturing of ceramic can be used. That's more for women's, luxury, watch industry, more for men, but clearly we used to have lots of demand of these people willing to make always more and more complex geometries. So in additive manufacturing, you can make lots of things. You have more freedom in geometry, in design. But you have limits. As all technology, you have limits. Everything is not possible. So sometimes you have to explain, no, it's not possible. Wall thickness more than 6 millimeters. You can print it, but you will have difficulty to debind correctly and burn all the binder. So that's one of the important limits of the technology also. And of course, you have to control the shrinkage during sintering. Shrinkage of around 20%, not exactly the same in the 3 directions. So that's all this know-how that we transfer to our customers who are investing in our technology. Defense companies, of course, has many applications with ceramics. Semiconductor business here, it's interesting because they are also willing to have big parts. I'm showing one of big parts also on my booth, but they need to have a very complex geometry with internal channels, with very good accuracy, and that's possible with SLA technology. So that was on SLA side. Let's focus now on MAT. So completely different technology. MAT means multi-additive technologies. So as you can see, it's a smaller printer. It's a desktop printer based on extrusion. Okay. Main advantage of this machine, small machine, cheaper price, of course. You have the possibility to have several extrusion technologies in the same printer. So you have FFF, filament. You can put a pellet head into the machine. Very interesting for people who are doing injection molding, because that's the same pellet that you use for injection molding. We can print it also, and pellet cost is very low compared to filament also. Robocasting or direct ink writing. And the main innovation is that we add in the same printer the possibility to do machining, CNC. We all know that extrusion, you always see the layers. That's a problem sometimes. So with CNC, in the same machine, you print, and you have the possibility to improve the surface roughness or improve the tolerance, dimensional tolerance of each part. On green stage, not sintered. And advantages, okay, you can manually switch from one print head, excellent finishing because you have the CNC possibility. You can print all the material you find on the market with filament, for example. We propose filament, but you can buy your other filaments. It's completely open source machine, so you can really have access to everything. And what is also interesting, low investment compared to SLA, that's true. And we don't have this difficulty of absorbing the light, okay? Silicon carbide, I told you that we cannot print it with SLA. We do not have any difficulty to print it with a filament. So that's the material available, okay, alumina, zirconia, silicon carbide. But you have also the possibility to print titanium, stainless steel, or copper. I have a short video showing printing and after machining. That's interesting to see also the tolerances we could get after machining. And you see the difference here without machining, here after machining. Example of silicon carbide parts. So my colleague in Berlin, Tivari, they have been developing this material, silicon carbide, in collaboration with ESA. It's the European Space Agency. Silicon carbide is really known and famous for aerospace properties. And we obtain a density close to 97%, which is quite good. To conclude, okay, we have developed, you have machine, we have expertise, we have training, advice, but what a customer needs now to switch to industrial and production, what we think is clearly automatization and machine learning for the next 10 years. What do I mean? We are working on automatization. With SLA, you have the possibility to do automatization, of course for printing, but also for cleaning, even debinding and sintering. So we are, I'm trying to, there is a short movie where we are working on automatic machine for cleaning, for example, also a robot putting the part in the debinding furnace and immediately after debinding again sintering. So clearly the objective is to decrease the cost per part. That's an issue we have. It's true that we need to find today markets where it's high value parts today. And what we also are convinced that we need to integrate artificial intelligence in our industrial printers. So we are now launching a new software able to support and help the customer to say, okay, I want to print this platform. You put this platform in the software and it will tell you, okay, you need to have to put these parts, more parts in the printing platform or remove parts. The support is not right. You should support like that. And this is the key point to help our industrial customers in the coming years. So productivity, repeatability is a very important when you evaluate technologies. You need to evaluate, of course, suppliers, financial solidity for the next 10 years is important. How we support you. Do we have local partners to support very quickly? That's a key point to have confidence and obtain good results with the technology. So objective is scale for us. Objective to scale on industrial printers, lower the cost per part, obtain good repeatability, automatization to reduce the cost per part and reduce also the human work in the process. That's what we believe for the future. I think that's the last slide. Muito obrigado. And if you have questions, do not hesitate.
So we are open for questions. Any questions?
Hi, Arnaud. Thank you for your presentation. I have one question. The Professor Paulo told us about the binding process is very difficult, and how the industry facing this problem to give the customers very good products, like you show us here.
Thank you for the question. We are working on debinding to reduce, for example, timing. Today, debinding is 3 to 4 days, so that's part of the process. It's due to the importance of quantity of binder that we have. More or less, it's 50% in volume binder. So you need to remove it. We are working, trying to reduce the timings, but at the moment, I think it's difficult to reduce it. And in the ceramic world, they already know this kind of limits, because that's the case also with injection molding. Injection molding, you have a high quantity of binder, so you have high timings of debinding. So yes, we are trying to develop collaboration with universities, with institutes to work on reduce time of debinding, but it's difficult and it takes time. After, you know, also debinding is 3 to 4 days. It's a short one. It can be much more. If you want to debind even very thick parts, you need to add to put a longer debinding stage. So we are working. We try we develop things with microwaves debinding, for example, to try to shorten it. But it will appear, but let us a little bit more time.
Hi, Arnaud. Thanks for your presentation. It's about debinding too, but it's about the porosity of silicon carbide. You show about the density is like 96.1,
yeah.
But about the porosity, how you can control after debinding this porosity in this ceramic?
With this technology, you know, you will always have porosity. You cannot, you know, when the nozzle is doing curves, you create porosity. So it's just linked to the technology. It will be difficult to again improve that. We achieved almost 97%. We are quite happy with that. We developed also this CNC also to decrease the porosity, because when you do machining, you remove defects and you improve mechanical properties. So that's what I can tell you, but it's linked really to the filament technology. If you want to have fully dense part in silicon carbide today, it's not ready.
Thank you for your very nice presentation. Concerning still the binding, you said you could take like several days, but what's the maximum wall size that you can get?
Today in alumina, what we say as a recommendation for our customers is maximum 6 millimeters sintered.
Okay, thank you very much.
But we use with collaboration with INSA in Lyon, we developed 10 millimeter how to say it, with more days in debinding.
After sintering?
After sintering, 10 millimeter. Okay. Yeah.
Great, thank you.
Any other questions? Okay, so thank you very much, Arnaud.
Thank you.
You have a gift for me? So, some short notes. I know everyone is hungry. I think I will speak in Portuguese and later I will translate for English. Senha do Wi-Fi, se vocês estiverem precisando, tem a rede EESC Visitantes, o usuário é Visitantes e a senha é EESC, EESC 2024, tudo minúsculo, tanto o usuário quanto a senha. So there's a network for guests, EESC Visitantes. The user is Visitantes. If you want, you can call me later. I can spell it. And also EESC 2024 is the password. I would like to remind you to vote for the best 3D printed part in the next coffee break. We got more parts in this last coffee break, so please give your vote for the best one. We are going to return at 2:30. Sorry, 2:30? No, at 2. Sorry, at 2:14. So remember that we're going to make a sorteio of one entrance to the Picanha na Tábua restaurant. And about restaurants, some suggestions for the students that registered up to August. We got not a partnership, but the restaurant of the university is open for you by 10 reais, so 10 Brazilian currencies, but only for the students that were registered before August. So you need to go to the side of the canteen and pay with cash, and they will give the entrance to the restaurant if you want to. Otherwise, there are other restaurants around. There are 2 restaurants inside USP, like some small canteens, one just like near us. There's also one outside the street called Salute, which is more healthy food. There's also Mamãe Natureza, which is healthy but has very different types of food. And if you want other suggestions, there's a near shopping center with many options. So I think you can find good options around. And if you want any suggestion, please ask the people in blue. Okay? So see you at 2. And have a nice lunch. Bom almoço a todos.